Chapter 14, Transformers. So as we go through transformers, you're going to see that what we're going to build on is what we learned in the previous chapter on inductors. Inductors and transformers have lots in common because they are actually coils. In this case, we have two coils that interact with each other with something called mutual inductance. So we're going to learn about stepping up and stepping down, loading the secondary winding, reflected loads, impedance matching, very important, ratings on transformers, tapped and multiple winding transformers in this section. So we will learn in these objectives what all of these terms mean and what the concepts are of each of these. Some new terms then, key terms, mutual inductance. Again, we use our acronyms and our abbreviations: L sub M, L for the inductance, M for mutual. So mutual inductance, L sub M. Transformer, primary, secondary, coupling, turns ratio. We use a little letter, little Greek letter for that, for the turns ratio. New and reflected resistance, impedance matching, apparent power ratings, and then something about a center tap. So when we look at transformers, we can see that we have two coils that are placed close to each other, changing electromagnetic fields that produce by the current in one coil and cause it to induce a voltage in a second coil. So we produce a coil and a current in one, it induces a voltage in the other. Okay, so by mathematics, we use the relationship that the voltage induced, that's the little IND, is equal to the inductance L by the change in time, or the change in inductance, the change in current with respect to time, the change in time. So V inductance is equal to L di by dt. A voltage is induced then in the second coil as a result of the changing current in the first coil, producing a changing electromagnetic field that links to the second coil. So we can see we have our lines of force or flux that cut through, that are created in the first by the applied source, that cut through the coil of the second, and that cutting of the second then produces a voltage. Then if it's a fluctuating source, in this case an AC source input, it creates an expanding collapsing relationship. Thus the corresponding induced voltage then we would measure on an oscope, and it would have the same sinusoidal relationship. The coefficient of coupling then, K, is that coupling between two coils, and it is the ratio of the lines of force or flux produced by coil 1 linking to coil 2. So you can see we use the Greek letter phi then from 1 to 2 as our shortcut relationship, and it identifies the total flux produced by current coil 1 into coil 2. So the coupling then, phi 1 to 2 divided by phi 1. In this case we have a ratio, so it's a unitless relation. In half of the total flux, if half of the total flux of the is produced by coil 1 links to coil 2, then the K, or the coupling, then is 1/2 or 0.5. The greater the value of K means that more voltage is induced in coil 2 for a certain rate of change of current from coil 1. So coefficient of coupling depends on proximity of the coils and the core material of the windings, also the construction and the shape. And this is things that we're going to find out about. So if we separate, all this is saying is if we separate those coils by a distance, we have less coupling. So there's going to be less induced. As we bring the coils together, we get more coupling, there will be more induced voltage. Also, if we have different materials between the windings, if it's air, if it's ferrite, if it's iron, whatever it is, it will change the coupling relationship. So one coil produces a total magnetic flux of 50 microwebers, and 20 microwebers link coil 2. What's the coefficient of coupling K? Well, plug it into the relationship. Phi 1 to 2 divided by Phi 1, 20 microwebers divided by 50 microwebers gives us a coupling coefficient of 0.4. So a little less than 1/2. Looking at the relationship then for mutual inductance, three factors influence mutual inductance: the coefficient of coupling K, the inductance of L1, the inductance of L2. Okay, so in this relationship, L sub m, the mutual inductance, K times the square root of L for the transformer. Okay, so you can see schematically, we've got L1, we've got L2, we've got some proximity between them. In this case, it looks like we've got a air space in here, the mutual inductance between the two, and the relationship for the coefficient of coupling. So two coils are wound on a single core. The coefficient of coupling in this case is 0.3, so it's way less than 1/2. The inductance of coil 1 is 10 microhenries. The inductance of coil 2 is 15 microhenries. What is the mutual inductance? So we use our relationship. L sub m is equal to K, L sub 1, L sub 2, multiply, take the square root, multiply times the coupling coefficient, and we get 3.67 microhenries as the mutual inductance between the two coils in the transformer. So we can see here our basic schematic symbols: primary 1, secondary 2. If we connect a source and a load to it, you can see we have a AC source on the input. We've got some load on the output, not defined. Okay, so this is your basic transformer relationship. The schematic symbols then, based on the core type, you can see here nothing in between, air core. These dashed lines identify iron of some sort, a ferrite core. And then if we have an pure iron core, so ferrite core is particles of iron or iron-like material, and if you see the two straight lines, that is a solid iron core material. High frequency transformers then are basically this type of configuration. Audio frequency and power transformers you're going to see as this type of relationship schematic. Transformers with cylindrical shaped cores then we would identify as something that looks like this illustration. You'll notice here we've got an air or a ferrite core. We've got loose coupling between the two because we've got a space between them. If we tightly couple the windings, we can see here we've got one laid over the top of the other, then we get more mutual inductance and more activity. An iron core transformer construction then with multi-layer windings is going to look something like this. You can see we've got laminated iron core that the windings are wrapped around, primary 1, secondary 2, or we can take and put them overlapping each other as shown in this explanation here. The shell type, both windings are wound on the same leg, where here we have them wound on separate legs. What do they commonly look like? Well, these are your illustrations of what a transformer might look like, and you can see that depending on the circuit board that you're dealing with or the chassis, typically this big monster here you would see on a chassis. Typically these here are going to be something you see on a circuit board. You'll notice the pins on them that identify a circuit board mount. So let's look at what the turns then of a primary and secondary have an effect. So we come up with something called the turns ratio. The turns ratio, lowercase n, is the ratio of the secondary in the numerator to the primary in the denominator. So these are the number of turns on a particular device. So if we look at an example here, a transformer primary winding has 100 turns. The secondary winding has 400 turns. So you can see 100 to 400. What is the turns ratio? So since we've identified them as secondary and primary here, 400 to 100, we put it in the relationship. The secondary divided by the primary gives us a turns ratio of 4 in this case. The direction of the windings then will have an effect on the output signal, primarily the phase relationship. The direction of the windings determine the relative polarities of the voltages. So in this case, you can see these dots identify the polarity relationship and will give you the phasing also. So the applied voltage for the primary, dot here. The induced voltage of the secondary, dot here. Notice that our phase and polarity match on the input and the output. If we show a depiction here of one dot on top, one dot on the bottom, now we have changed the polarity, where we have positive to negative. Here we have negative to positive going polarity. If we look at it on a schematic diagram, the phase dots then indicate the relative polarities of the primary and secondary voltage. So you can see dot, dot, match, match. Dot, dot, input, output is out of polarity or phase. So if we want to look at the relationships to stepping up and stepping down, this relates to the input versus the output. If we want a larger output on our transformer, we step up. If we want a lower output, we step down. If we want them to be the same, we don't do either, okay? So in this case, the voltage of the secondary divided by the primary is equal to the turns of the secondary divided by the primary. So they match here. If we want to determine then the relationship or the ratio, so the turns of the secondary divided by the turns of the primary equals the voltage of the secondary divided by the voltage of the primary, then we can see that the number of the ratio will equal the voltage relationship as well. So N will equal the secondary by the primary, or we can determine the voltage output, the secondary, as the ratio times the voltage primary. So what's the voltage across a secondary winding? The turns ratio being 3. So we can see in the diagram here, we've got a 1 to 3 relationship. We've got a primary source of 120 volts RMS, and we need to determine the output voltage. So the output voltage V secondary is equal to N V primary, or 3 times 120, which gives us 360 volts. So you can see we've got a step up transformer. In this case, we've got a 5 to 1, same input voltage. Okay, the transformer has a turns ratio of 2/10. What's the secondary voltage? The secondary voltage then is 2/10 times 120, which gives us 24 volts. So now we have a step down transformer. Okay, so in the next section when we come back, we're going to look at something called DC isolation. How do we use a transformer to isolate one part of a circuit or one signal from the other when we do not want a direct application of the input signal to be part of the output signal?